Hello everyone, this is Gary Templeton. In this video, I will cover Module 2 on multivariate techniques. I will describe several tests of linear association between variables. There are two broad classes of these empirical assessments, correlation and regression. I will review several basic procedures and conclude with a walkthrough of the Module 2 dataset activity, which involves logistic regression. A correlation coefficient is a numerical measure of a statistical relationship between two variables. The correlation coefficient is the most basic way to empirically determine the relationship between two variables. In calculating the correlation coefficient, neither of the two input variables can be purely categorical. There must be a hierarchy of values in the measure. As with interval and ratio data, there are two basic types in common use. First, Pearson's R is mainly used for two variables characterized by asymptotic normality or near normal distributions. Second, for variables departing from normality, the Spearman's rank is preferred. Thus, Pearson's R is considered a parametric option and Spearman's rho is considered a non-parametric option for assessing the relationship between two variables. In either case, the correlation coefficient is interpreted the same. Both statistics range from -1 to 1, with 0 implying no relationship between the variables. A perfect -1 correlation coefficient means the two variables are perfectly negatively related, while a value of 1 represents a perfect positive relationship. This graphic shows perfectly negative, 0, and perfectly positive correlated data. Here is perfect negative correlation, perfect positive, and no correlation whatsoever. It also shows other positive and negative value scenarios. Linear regression is named such because it assumes and is interpreted as there being a linear relationship between a dependent variable and one or more independent variables. As you can see here, linear regression models include additional information that the correlation coefficients do not. It shows the nature of the relationship. In this case, it would be a positive relationship. But it also shows a y-intercept. This is the x-axis and this is the y-axis. And you can see that where the x values are 0, the response variable or dependent variable is at 5. This value is called the constant in a regression equation. The slope here is called the beta coefficient in a regression equation. When a linear regression contains multiple independent variables, there will be multiple beta coefficients, and this graph will get a lot more complicated. It will be as complicated as there are number of independent variables. Later in this presentation, I will show you a depiction of this type of scatter plot with multiple independent variables. It's important to talk about the assumptions of linear regression. The first assumption is normality. Your book talks about the importance of a normal distribution as a characteristic of the dependent variable. Linear regression is most appropriate when the data is asymptotically normal. Again, that means near normality. If the data is not, researchers should consider other classes of regression, such as ordinal, partial least squares, nonlinear, or, as will be explained later, binary logistic regression. Thus, the distribution of variables will influence the regression technique used. As the name implies, linear regression also assumes linearity between the x and y variables. You can see in this diagram on the left, that implies a positive linear relationship. The next one is a negative linear relationship. And the graph on the far right shows a nonlinear relationship. In the case of a nonlinear relationship, it would be appropriate to change the distribution of one or two variables through transformation in order for the regression equation to adhere to this assumption. Another linear regression assumption is independence of values. This mainly comes into play when there is time-ordered data. What we're trying to do is make sure that time shouldn't be a variable included in the analysis as an independent variable. When you chart values over time, you don't want a variable to be partially determined by time. So in this top graphic, you can see that time does not affect the value. In the middle graphic, you can see that time does affect the value. In that case, the values are dependent on time. Time can have a positive or negative association with the variable being evaluated. Another assumption is multicollinearity. This is a concern when you have multiple independent variables or variables you're trying to use to predict the dependent variable. We want the independent variables to be, as their name implies, truly independent. We don't want them to be correlated with one another. That is because they will explain the same phenomenon when they are, indeed, empirically correlated with one another. We want unique independent variables that explain different concepts. That will make our regression equation more reliable over subsequent samples. Another linear regression assumption is homoscedasticity. As you can see from this graphic on the left, the variance of values is much tighter over this range as values are smaller on the x-axis than when x grows. When x gets larger, the variation increases. We don't like that in linear regression because that means that values are interpreted differently on the left-hand side of the timeline than the right-hand side because variances change. Same with this middle diagram. You can see that variance changes over different values of x, so we can't interpret along the x number line the same. Ideal is what we call homoscedasticity on the right-hand side, where we have consistent variance on the regression line. I'm going to give you a brief example of simple linear regression. I showed you this diagram earlier, and this is a depiction of simple linear regression, which means you have one x or independent variable, and with that you're trying to explain a y or response or dependent variable. Simple linear regression is similar to the correlation coefficient in that it evaluates the linear relationship between two variables. However, simple linear regression designates one variable as the dependent variable, i.e. the outcome or response variable, also designated as y, and the other as the independent variable, also termed the predictor and designated as the letter x. Shown here is the output of regressing green vegetable consumption as the predictor variable on BMI or body mass index as the dependent variable using your Chapter 13 SPSS dataset. The model fit can be ascertained from the model summary table. This table reveals the model R-squared value, which ranges from 0 to 1 and depicts the level of association between the two variables. As shown, the test did not produce evidence that green vegetable consumption explains BMI. As you can see, the R-squared value is 0.000, which means the two variables are completely uncorrelated. The ANOVA table shows the same thing with a significance value of 0.915 indicating no association. If there was a significant relationship found, the output also produces a highly informative regression equation in the SPSS output table named coefficients. Here we can see that the unstandardized beta value for the constant, also known as the y-intercept value on a scatter plot, is 27.492. This means that when the independent variable, green vegetable consumption in this case, is 0, the BMI averages 27.492 in the sample. The table also shows that the unstandardized beta coefficient for the independent variable, again green vegetable consumption, is 0.003. This is shown here. This means the relationship is positive. However, the significance value of 0.915, shown here, indicates that green vegetable consumption does not associate well with BMI. Thus, the model indicates there is no significant relationship between the two variables, a potentially insightful scientific finding. However, the researcher's job may be incomplete, as the possibility of variable transformation remains an option in subsequent reformulations of the model. Another option is to add independent variables that theoretically should also associate well with BMI. Multiple linear regression is an extension of simple linear regression in which more than one independent or predictor variables are entered into the analysis. Interpretations of multiple regression findings are much the same as with simple linear regression. However, as the name implies, multiple linear regression equations will be represented by multiple beta coefficients and significance values, one for each independent variable. A single R-squared value will be reported and interpreted the same as with simple linear regression. Multiple linear regression is considered more powerful because more variables are leveraged to explain the dependent variable. Also, all predictors may be tested simultaneously, which means each beta coefficient can be interpreted in the presence of every other model independent variable. Multiple linear regression is appropriate when the variables are continuous, measured at the interval or ratio level, or using a binary independent variable. You can see from this diagram the multidimensional nature of multiple linear regression. Like simple and multiple linear regression, logistic, also called logit, regression uses linear interpretations. In other words, the dependent and combination of independent variables are explained as having a linear relationship. However, logistic regression uniquely utilizes a binary dependent variable. You would use logistic regression when your dependent variable is binary and when you have one or more independent variables. For example, Shetty and Shetty in 2013 studied factors believed to predict breastfeeding behavior in India. Classes of binary regression models in nursing may involve predicting whether students will pass or fail a test or whether a medical outcome is healthy or sick. Because the response or dependent or y variable always has limited variation because it's a binary variable, binary regression models have special challenges when we try to replicate their results. For that reason, special adaptations have been established to investigate the relationships. Such special topics include using binary independent variables, transformations of the dependent and independent variables as described earlier, and the evaluation of log odds ratios in the interpretation of results. Logistic regression is the focus of our Module 2 dataset activity. I will walk through that activity next. The first thing you need to do is download the dataset, go to the module in Canvas, and assuming you have SPSS installed, go ahead and click the link. This may take a minute to download the file. And here's the dataset. We're going to do logistic regression, and this involves using a dichotomous dependent variable, or a dependent variable that is binary, and another way of saying this is that it has only one of two values. Because distributions are important in selecting your regression approach, I want to show you the distributions in this dataset. To do this, we go to Analyze, Descriptive Statistics, and Frequencies. We can push all of the values over there to the right to evaluate. We're not necessarily interested in this time at a frequency table, so we'll turn that off. We go into Charts and Histograms. Right now we're not interested in a normal curve, so we won't select that. Press Continue and OK. SPSS will output a histogram, which is a graphical display of the distribution. For example, each one of these bars is a count of values for that instance. For example, this is a count of zeros, and this is a count of ones. And you can see from this is a dichotomous variable, either a 0 or a 1. Scrolling down, that's gender. Scrolling down, we can see whether or not someone tried to lose weight in the past year. Either they did or they did not. That is a 0 and a 1 also, and as you see, the histogram shows the count of each. Scrolling down further, we see something that is not dichotomous. This is what is called a continuous variable, although the distribution is quite choppy. And each one of these bars is a count of values. As you can see, this variable departs significantly from normality. Scrolling down further, we see BMI. This looks closer to a normal distribution. And as you can see, it is not dichotomous. There are several values that it can be. Scrolling down further is another binary variable related to whether or not the subject tends to eat out or not. 0 or 1, that's a dichotomous or binary variable. So as a dependent variable, if we were trying to predict any one of these dichotomous variables, and we see 3 of them, we can include any one of those as the dependent variable. According to the assignment, we're going to run a logistic regression model looking at the association of having tried to lose weight in the past year. So in other words, we're trying to predict whether or not someone is willing to try to lose weight. We're going to predict this dichotomous variable with gender and BMI. Gender, as we saw, is a binary dichotomous variable. BMI is a continuous variable. So let's run that analysis. To run logistic regression, click on Analyze, Regression, Binary Logistic. The dependent variable, or the outcome variable, is whether or not the participant tried to lose weight in the past year. As stated in the assignment, the covariates are BMI and gender. The logistic regression procedure in SPSS will assign dummy variables for any binary covariate. In other words, if gender is binary, which it is, SPSS will generate dummy variables for it as necessary in the logistic regression equation. This will not be done automatically in ordinary least squares regression. But in order to do this, we have to tell SPSS that gender is a binary variable. So we go to categorical, we click on gender and move it over, press continue. Note that gender now has cat written to the side of it, short for categorical. Another thing we can do is inspect the confidence intervals. Click on options, click here for CI or confidence interval for exponential of the beta regression coefficients, and press continue. And now press OK. Based on the assignment, we need to determine whether or not the model is a good fit for the data. The model chi-square is what we use to determine the statistical significance of the overall model. This value is equal to the log likelihood of the alternative model minus that of the null model. The null model contains no predictors. The model chi-squared is found in the part of the printout labeled Omnibus Tests of Model Coefficients, where the chi-squared and its significance are reported. To get there, you will need to scroll down to this part of the report, and you can see it here. Chi-squared and significance values are provided for three methods: step, block, and model. Since all variables were entered together in this analysis, these values are the same for each method. This will happen when you use the default method in SPSS as we did. Based on the output, the chi-square is 73.242 with 2 degrees of freedom, and the p-value is 0.000. This indicates that the model, including 2 independent variables, is significantly different from the baseline model containing no independent variables. The results for the baseline model are shown in block 0, and the results for the model containing the 2 independent variables that we're interested in are contained in block 1. To examine the overall amount of variation in the dependent variable explained by all independent variables in the model, we inspect the Cox and Snell and Nagelkirk R-squared values. According to Cox and Snell, the independent variables explained 14.1% of the overall variance in the dependent variable. That is, gender and BMI explained 14.1% of whether a subject attempted to lose weight in the past year. According to Nagelkirk, the model explained 18.8% of variance in the dependent variable. The next 2 questions ask you to interpret the odds ratio and p-values associated with each independent variable included in the analysis. That is questions 2 and 3. To do this, what becomes really important is the odds ratio. Look in the output labeled Variables in the Equation in block 1. This table shows the regression coefficients, or B's or betas, the statistical significance of each independent variable, and the confidence intervals necessary to answer this question. First, we look at regression coefficients. In all multiple regression outputs, the beta coefficients can be used with the constant value to create a prediction equation. However, to do this, we must know a subject's code on each variable. We must know what each value means. To interpret regression coefficients from our logistic regression equation, it is critical to note how study binary variables were coded. First, for the dependent variable, whether weight loss was attempted in the last year or not, 1 is equal to yes. In other words, weight loss was attempted. 0 means no, weight loss was not attempted. In other words, as this value goes up, it implies greater effort at weight loss in the last year. You can see this in the output explicitly by scrolling up and looking at the dependent variable coding, where 1 is equal to yes, weight loss was attempted in the last year, and 0 is no, weight loss was not. While we're here, I can also show you that the other binary variable in the analysis, gender, was coded in this way. You can see that male was a 1 and female was coded as 0. This coding of binary variables will greatly impact how we interpret the results. So understanding this is essential before we interpret our model using odds ratios. Scrolling back down, also note that in logistic regression, beta values are used to determine the odds ratios, or the ratio of one probability to another. In this example, the odds ratio is the probability a subject did attempt to lose weight, in other words, the dependent variable equals 1, among males, where gender is equal to 1, divided by the probability a subject did attempt to lose weight, where the dependent variable is 1, among females, where the gender is 0. The column labeled exponential b provides adjusted odds ratios and associated confidence intervals. For these odds ratios are shown to the right. As you can see, the associated p-values for gender and BMI are both less than 0.05. This is evidence that, based on this sample, the null hypothesis that the odds ratio is 1 is not supported. Thus, because the significance level is reported at 0.000, we can say that the sample data suggests that this independent variable, or gender, does help explain the dependent variable. In addition, the confidence intervals provide similarly helpful information. In both cases, neither interval includes 1. If you look at these two intervals from 0.328 to 0.723, for example, for gender, 1 is not contained within that interval. This is further evidence that the null hypothesis, that the odds ratio is 1, is rejected. To the contrary, the sample data suggests that the odds ratio is not 1. Because of this evidence, we believe the odds ratio indicates that the independent variable does explain the studied dependent variable. In other words, gender and BMI do explain whether or not someone tried to lose weight in the previous year. Note that the confidence intervals for the gender odds ratio are both below 1, and for BMI, both are above 1. This is shown here. For gender, we are confident that the odds ratio is less than 1, which means that the odds of attempting to diet or lose weight in the last year among men are 0.487 times lower than that of women, adjusting for BMI. Note that this interpretation is because men were coded at 1. If women were coded at 1, it would have been interpreted in the opposite manner. BMI should be interpreted differently, since 1, it is a continuous variable, and 2, both confidence interval values are above 1, implying a positive relationship. The significance and confidence interval values give us confidence that increasing BMI increases the odds that a subject attempted to lose weight in the last year. Specifically, by increasing BMI by 1 unit, on the average, the odds of trying to diet in the last year increased by 1.143 times, which is shown here, or 14.3% with gender included in the model. I hope you found this to be useful. Thank you.